Alright, chapter 7 and 8 is about circular motion and rotational equilibrium. Starting off, tangential velocity and centripetal acceleration. First question relates directly to math class. In reference to circles, what is a tangent line? And you would say that a tangent line is a straight line that touches a circle without intersecting it. So if I take this circle that I have here, this line here is now a tangent line. It touches the circle that the Death Star is going to orbit without intersecting it. So applying that to what we're learning about and say here. So tangential speed, what is that? The straight line speed at or along any tangent line on a circular path. We would call it VT, tangential velocity. And what that means is, at any moment as this Death Star orbits, it is following a ever-changing path. At this moment in time, the Death Star is traveling downward as I rotate it counterclockwise. It is traveling downward. At this moment in time, it is traveling sideways. At this moment in time, it is traveling upward. And here at the top, it is traveling off to the left. At that moment in time, it has a certain tangential speed. We'll call it VT, tangential velocity. T is that. It's not time. So often people confuse that as a time, and it's not a time. Now, there's another kind of velocity we can also discuss. We could discuss angular velocity. Angular velocity would be the speed around the circle, but aside from the very next slide, we're really not going to talk about angular velocity other than just what it is. We will not calculate it. If you see it in a book, it will be listed as a little w, that is a Greek letter omega, but we will not be calculating that angular velocity in any way. Let's look at some examples. Tangential velocity and angular velocity in comparison with one another. So kind of tote that up there. First off here, tangential velocity is the linear velocity of the object, meaning in one line, how fast is it going? Angular velocity is the velocity of an object around its path. So tangential velocity is linear, so we're going to talk about meters per second when we talk about tangential velocity. Angular velocity is circular, so we're going to talk about revolutions per time. So when you look at a record playing, you can look at it as saying, oh, it revolves this amount of times in a given minute. When we talk about vinyl, of course, a CD, you see RPMs on things, and in an engine, you see RPMs. That's revolutions per minute. With a car, RPMs is in the thousands, so they're making thousands of revolutions per minute. With a CD, they make many, many RPMs, and honestly, I'm just trying to look on my computer here. I'm not seeing any RPMs listed on anything. Oh well, they go fast. So let's look at this example. I got these three Death Stars all linked up. The yellow and green one here on the outer path, the yellow and green one on the outer path, as they move, you could easily say that they are all moving together, that they have the same speed around the path. If you say that they have the same speed around the path, you are referring to their angular velocity. They both have, if it took them 1 minute to make their loop, they would both have an angular velocity of 1 revolution per minute. However, it is easy to see that the green circle is much larger than either the gray or the purple. Therefore, the yellow and green Death Star has a much higher tangential velocity because it has to cover a much greater distance in the same amount of time. So just look at this from, if you're looking at arcs like you would in math class. If we go to this point here, just look. As these Death Stars traverse from straight sideways to this point, even though, they're a little goofed up, But still, look at how much farther along the green line we went compared to the gray, compared to the purple line, in that same amount of time. You could easily say that the green one's going at least 4 times as fast as it orbits around. Its tangential velocity is much greater because it is covering a far greater distance in the same amount of time. So enough about that. Let's talk about acceleration. Now I want you to think about back to chapter 2 when we talked about the definition of acceleration. Acceleration is changing one's velocity. To change your velocity, you can either change your speed or you can change your direction. In this chapter, we're going to talk about things that are keeping a constant linear speed. Okay, they are not going to be speeding up or slowing down. However, as these things accelerate, their direction is constantly changing. And we need to talk about what that means. What direction is it accelerating? Now imagine if I was in front of you and I had a tennis ball on a string, which I do, and I will spin it around, I am sure you, in front of class. As I spin it around, at any moment in time, it is changing its direction. You got to think about which way is it changing its direction. So there's another visual for you. There's a tennis ball spinning on a string in front of you at a great amount of speed. What direction is it going? Well, let's look here. Centripetal acceleration is what we're talking about. Centripetal acceleration is defined as the acceleration of an object toward the center of its path. Now think about that tennis ball as it circles. If at any given moment in time it is not accelerating towards the center of the path, won't it go somewhere else? Think of this Death Star in the picture. At this moment in time, it's heading off at this diagonal. A little while later, it's heading off straight up. If it were to somehow come undone from its gravitational pull on the planet Alderaan, if it did that, the Death Star would instead start moving off in this path. But it's indeed accelerating. If its acceleration was outward, let me move it here to the middle, it's a little easier to work with. If the acceleration was outward, it wouldn't curve this way. I mean, when do things accelerate away from their path? If its acceleration was forward, it would continue to go forward. It doesn't do that. It circles. So think about it. Think about it. If the acceleration is instead toward the middle, in this moment, it causes the Death Star to turn a little bit to the right. It moves a little more over to here. It still accelerates towards the middle. It causes it to turn a little more to the right. And it would continue to accelerate to the right. Well, eventually it wouldn't be to the right anymore. But it would continue to accelerate in towards the middle the whole way. This would keep it going in a circle. So which way is the Death Star accelerating? As it circles, it is always accelerating inward. This is centripetal acceleration. Right there. Centripetal acceleration. That's what it is. It's always inward. And here's our equation to find centripetal acceleration. Centripetal acceleration is equal to tangential velocity squared divided by the radius of its motion. And we're talking about a legitimate radius here. Math class, center to the outside. Okay? So, what are we going to do with this? Well, of course, it's going to rotate, and there's homework. 226, 1 through 4. Did you catch that? 226, 1 through 4. Oh, there it is again. 226, 1 through 4. In this homework, just make sure that you are being very aware of what the radius in the circle is. Think about, are they giving me a diameter or are they giving me a radius as you go through it? Using that, you can figure out, the acceleration or the velocity or the radius.